So far what we have considered are what is called harmonic vibrations or harmonic effects, in that we have considered the force or the potential between two atoms to be varying as x square and the force between two atoms to be proportional to the displacement between them. If I were to plot them, the harmonic potential looks like this. It is going as x square as the atom's distance changes. However, in real life it is not always x square, it changes. In particular, it may become slightly softer as you go farther out, so that I can write V x taking only the next correction into account as some constant, let us call it k 1 x square minus another constant k 2 x cubed, and there could be higher order terms, but I will stop at x cube, and when I put this minus sign, that means the potential is becoming softer, and that has interesting effects. Consider this: suppose an atom is in the harmonic potential x square. If I include the x cube term on one side, as x increases, the potential will, on one side as x increases, the potential will become smaller, because minus g x cubed, and on the other side, because x cube will be negative and minus will make the potential larger. So, it will become asymmetric. Now, imagine an atom here which is oscillating back and forth. Let me make this atom by orange, and it was oscillating back and forth. As I increase the energy of the atom, it goes back and forth, but is symmetric about x equals 0, and therefore, its average x remains 0. On the other hand, if the potential was anharmonic, that is shown by green, then the atom would spend more time on the right hand side and less time on the left hand side as its energy is increased, and therefore, x will tend to increase as T increases, because as T increases, the average energy of the atom goes up and it will shift towards softer side of the potential. Notice what we have said. What we have said is, if crystal is harmonic, that means the interaction between atoms is harmonic, there will be no thermal expansion. So, an harmonic term in potential is needed if thermal expansion is there. So, there are these anharmonic terms, we need them to explain thermal expansion. So, this is one effect of thermal expansion. The other effect, which in particular I want to talk about, is that it changes the thermal conductivity, what is known as Umkclapp process, and this is something new that you should know about. So, I will talk about these two things in the context of anharmonic term in the potential, and two things that I am going to talk about is, number one, thermal expansion of a solid, And the other thing that I am going to talk about is what is known as Umkclapp process, and this affects thermal conductivity. So, let us talk about thermal expansion first. The potential energy is given as, let us say, K1 x square minus K2 x cubed. And if I want to calculate the average x, this will be x times probability of particle having displacement x, and then you integrate it over all the x. And this, taking the Boltzmann factor into account, is going to be minus infinity to infinity x e raised to minus Vx by kb t dx divided by the total probability, which is 1. So, I have to normalize this whole thing, e raised to minus Vx over kbt dx. Let us now put in the expression for Vx, and then we get x equals integral minus infinity to infinity x e raised to minus k1 x square minus k2 x cubed dx divided by minus infinity to infinity e raised to minus k1 x square minus k2 x cubed divided by kb t divided by kb t dx. And I want to just retain terms up to first order in K2. Now, K2, the anharmonic effect we are taking to be much smaller than K1, and that is pretty okay, because experimentally what we find is that the first term itself explains a lot of things, as we have been doing in the past few lectures. Now, this thermal expansion comes about, which is a very small number, and that is affected by K2. So, K2 is much smaller than K1. So, therefore, what I am going to do is retain e raised to minus K1 x square as is, and take e raised to K2 x cubed as 1 plus K2 x cubed, and keep terms only up to linear in K2. And therefore, I can have x is equal to integral minus infinity to infinity x e raised to minus K1 x square plus minus infinity to infinity K2 x raised to 4 e raised to minus K1 x square dx divided by, I have already taken care of this K2 here up to linear term. In the denominator, the lower term, I will just neglect K2 x cubed term. Even if I retain it, it will go upstairs as some K2, and then I can just ignore it. So, I have expanded this up to K2, and in the lower term, I will just keep the quadratic term minus infinity to infinity e raised to minus K1 x square over kb t dx. I have forgotten kb t here, dx divided by kb t dx. Now, as we have argued earlier, if you keep only the harmonic terms, it does not give you any expansion, and you can see it right here that this term out here is odd in x, and therefore, this integral is actually 0, and therefore, I have average x is equal to K2 integral x raised to 4 e raised to minus K1 x square dx minus infinity to infinity divided by integral minus infinity to infinity e raised to minus K1 x square dx. There is a divided by kbt, which I keep forgetting. And you can see that x is now increasing. This number is non-zero. So, if I include this x cube term, x is increasing as temperature goes up, because as temperature goes up, this term becomes smaller and smaller, and therefore, this integral becomes larger and larger. In fact, this problem I will give you in the assignment is that you can integrate this very easily, x raised to 4 e raised to minus k 1 x raised to x square over k b t dx, and so you can the other integral e raised to minus k 1 x square over k b t dx, and when you do this division you get x proportional to t. So, the distance between these atoms increases linearly with temperature, and this is what you find in thermal expansion. If you include higher order terms, there may be some corrections, but this is the first correction, and so what you realize is that anharmonic terms are important, in fact are responsible for thermal expansion. You may be wondering why I dropped the anharmonic term here. Even if you include that, it will be proportional to k 2, and if you take it through binomial expansion to the numerator, since the first term is 0, this does not have any effect on our answer. So, I could easily neglect that. I have made these statements, I would like you to confirm those. Second thing that I want to address now is the thermal conductivity, and this time thermal conductivity due to phonons, that means due to atomic vibrations. The first answer is exactly the same as in electrons. In electrons, when you had a solid, and Professor Banerjee has already derived this, if I had these electrons moving from one end to the other, when there was a temperature gradient from T1 to T2, one saw that the current, heat current, was minus the thermal conductivity dt by dx, and the thermal conductivity answer came out to be 1/3 the heat capacity, the average velocity of electrons times the mean free path. Now, change this picture to phonons, and what you will find is that if I think of these phonons like photons, like electrons, particles carrying heat, which vibrations certainly do, from one end to the other, I will get exactly the same answer. If I go from T1 to T2, the thermal conductivity due to phonons will be 1/3 C V L, where C is the heat capacity due to phonons, which we have already derived, V is their average speed, which you can take to be the speed of sound for acoustic phonons, and L is their mean free path. Why does mean free path arise? Because these phonons are scattered by imperfections in this lattice. So, there is a phonon which is coming in, it may get scattered, just like electrons were getting scattered due to imperfections in the Drude model. So, this is the standard formula. Now, how does anharmonicity affects? It affects. So, what I want to answer is how does it affect the thermal conductivity? Let us explore that. Suppose there are anharmonic terms, what will happen to phonons? Now, you see, if there are these only harmonic terms, you have studied in your 12th grade, waves move around without interfering each other. So, in harmonic approximation, when crystal is taken to be perfectly harmonic crystal, waves and therefore phonons pass each other without disturbance to each other, and what we mean in technical language, I will cut this disturbance and say without scattering each other. So, a phonon comes in, other one comes in, and they go through. They do not really scatter each other, they may interfere because these are waves, they interfere, but after that they pass through. What enharmonicity does, enharmonic term, and this I am not proving, I am just saying it, makes them scatter from one another. Why? Because you can think of enharmonicity makes phonons interact, not just interfere, but interact with each other, and when they interact they scatter each other. Now, let us see what happens in this scattering. We have discussed earlier, if there is a phonon of crystal momentum K1 coming in and there is a phonon of crystal momentum K2 coming in, they may combine due to this enharmonicity and you may finally get a phonon of crystal momentum K3. At low temperatures, phonons of low energies are excited. If phonons of low energies are excited, then K is also very small. So, what happens is low energy phonons interact with each other. So, suppose I have a Brillouin zone, one low energy phonon comes in, another low energy phonon comes in, and you get a final K which is very small. These are known as normal, or in short N processes. So, even if the phonons scatter or combine together, after this interaction they still continue to carry energy forward in this normal scattering or normal process. On the other hand, let us look at what happens at high temperature. At high temperature, now I have high K phonons also. So, what could happen is I have a phonon coming in, I have another phonon coming in, and they combine into a K which is very, very large. In fact, it may be so large, and I will show it with green, that it may be going outside the Brillouin zone. So, this is of K final K3. This K, however, is equivalent to, I can subtract 2 pi from here, this K is however equivalent to K at this point, where this is 2 pi by A, because all K's are equivalent to modulo 2 pi by A. Now, notice this, by this scattering I created a very large K3 which is equivalent to a K out here which is negative K. And what does that mean? When these two phonons interacted, they were carrying momentum in one direction or energy in one direction, and after they interacted made a new phonon which could be going the other way. In effect, you have stopped the heat, and not only you stopped it, you made it flow the other way, and this reduces the conductivity. This is known as Umkclapp. Umkclapp is a German word which means flip over. So, the two phonons which are going in one direction have flipped, made a new phonon which is flipped over. It starts taking the heat the other way and it reduces conductivity. So, at high temperatures, because of Umkclapp process, the conductivity may go down, and this is a purely enharmonic effect. If the phonons did not interact, they would not have this process. So, let us see what should we expect on the basis of all this for the conductivity of an insulator on the basis of the formula K equals 1/3 C V L, where C refers to the specific heat due to phonons, V their speed, and L their mean free path. At low temperatures, where normal processes take place, where the collisions take place, but the phonon wave vector resulting phonon wave vector does not go out of the Brillouin zone, L would be determined by the imperfections, and at low temperatures C goes as T cubed. Velocity of phonons is like velocity of sound. So, I would expect that thermal conductivity with temperature should rise like T cubed. However, as the temperatures go up and we would expect increases, we would expect when K larger than half the Brillouin zone size start dominating or start coming into the picture. That means K roughly equal to K d by 2, because by d by wave vector all the modes are exhausted. So, we will take that to be roughly the size of the Brillouin zone, or omega greater than or equal to omega d by 2, we will start seeing Umkclapp processes. And at this point, the mean free path would be determined by Umkclapp processes, mainly if they start dominating. So, in this case, the mean free path L would go as 1 over the average number of phonons, and at large T, C is roughly a constant. Number of phonons is 1 over e raised to h cross omega by k t minus 1, which can roughly be written for large temperatures as k b t divided by h cross omega. Therefore, if you collect it, you will have L, which is proportional to, we are saying 1 over n, will be proportional to 1 over t. So, mean free paths will start going down. So, if you collect the picture, what we will have is T, the conductivity as a function of temperature, it will go up as T cubed, and at a certain temperature around theta d by 2, it will start going down as 1 over T. So, this is the behavior one should expect for the conductivity of an insulator when Umkclapp processes start dominating. And this is again a result which is confirmed experimentally, and I will send you the results in a supplement to this lecture. So, finally, to conclude, we have completed in these 2 weeks the vibrations of crystals. We have introduced the concept of phonons, which are nothing but quanta of vibrations, and through these we have also studied the CV for crystals as well as thermal conductivity for crystals. Now, in the next week and following weeks, we will be switching over to the electronic properties again, and I will discuss Bloch's theorem and things like those. Thank you.